Hello and welcome back. I want to talk now about the Hough transform. The Hough transform is a really nice technique to detect objects, to segment out objects for which you know their shape. Maybe a straight line, maybe a circle, as we have seen in the previous example. For example, we want to detect the ball. We know it's circular. So can we include that information in our detection, in our segmentation technique, to detect that it's actually circular? Can we use the information that we are expecting here, a straight line, and basically get a straight line? So the Hough transform allows us to do that, and in a very simple and really nice fashion. Let's illustrate that. The basic idea is quite simple, and we're going to start with ideas on how to detect straight lines, and then we're going to move to circles. But starting with straight lines makes it much easier to understand. In school, probably in elementary or middle school, you have learned how to represent a straight line that is on a plane. And I'm going to write down the equations and explain them to you again. So here we have the plane. This is the image plane, the XY. This is the image plane, and we have points on a straight line on the plane. For example, this straight line might be this one or this one. Now, a straight line on a plane is represented, can be written down in the following form. We have rho, and I'm going to explain each one of these symbols in a second, is x cosine theta plus y sine theta. So, rho is the distance from the coordinate system's center to the straight line. And this should be perpendicular, of course. It's a distance. Might be a bit tilted in the video, but it should be basically a 90 degrees angle. So rho is the distance to the straight line, and theta is this angle here that basically is the angle with one of the axes. Let's pick this one in this case, with the line connecting the center with the straight line that we are considering. So basically, every point that is on the line holds this equation. Every single point, this one, and every point in the line will hold this equation. Using that, here is the idea of the Hough transform. We take a point on the image, and that comes from the edge detection. So basically, every point that the edge detector said there is an edge going through. For every point, we basically have an infinite number of lines going through it. This is one of them with a particular rho and a particular theta. Now let's draw a different one. This line has its own rho and its own theta. This will be rho, this will be theta. We can go and draw a different line. All the lines going through the point. So here is another one. It has its own rho here and its own theta. And we can keep doing that. We can pick yet another one. For example, let's just pick this one. And it has rho and it has theta. So every point has an infinite number of lines, and basically every point will go and say, any of those lines is okay with me. The point will go and vote for rho and theta, for a series of them. It should be voting for an infinite number, but we're going to discretize. We're going to do this in the computer, so we won't be able to vote for an infinite number. We're going to vote for a discrete series of rho and theta. Now, that's only one point. And basically, every possible line that goes through that point will get one vote. Okay? Now, what happens with this other point? This other point has its own lines that go through it. So it's going to go and vote for its own lines. It's going to vote for this one, of course. But it's also going to vote, for example, for this one that has its own rho and its own theta. And it's going to vote, and I don't want to draw too many because it will make the picture very unclear, but it's going to vote for another line here, and so on. So it's basically gonna vote also for a series of rho and theta. And all the votes will get one vote. But look what happened. This line is common to both of them. And we know that in Euclidean space, through 2 points, there is a single line. So there's only one line, the one that we are looking for, that's going to get 2 votes. Basically, and that will help us to understand what's the rho and the theta for this line. But of course, not only 2 votes, because there's going to be another point here that is also going to go vote for a series of rho and theta, but it's going to vote for this one. So this one is now getting 3 votes, one for each point that the edge detector found that is on that line. Now, of course, the edge detector might find points that are outside of that line, and those will also make their own votes. But hopefully, the only line that gets a large number of votes is the line of interest. So that's the basic idea of the Hough transform, and we're going to provide more details in a second. But every point that the edge detector found votes for the possibilities, in this case, lines. If we have multiple points on the same line, then we're going to have multiple votes. So how do we do that in reality? So in reality, we are going to go from the XY coordinate system, which means the image coordinate system, to a new coordinate system, which is theta and rho. That coordinate system, the same way that our image is discretized, it's going to be discretized. So theta can be anything around the circle, and we basically discretize as fine as we want, or as fine as our memory or our computational time allow us. Let's say we can discretize every 1 degree. We do the same for rho. We discretize it. We know that rho cannot go farther than the size of the image, so we know it's bounded. And then we basically discretize it. And then what we're going to do, let me write the equation again. We have the equation rho x cosine theta plus y sine theta. So what we're going to do is the following. We go to every point, let's say this one. So every point gives us xy, the coordinates of that point. Then we run through theta and we say, let's say 1 degree. So we have the coordinate x and y. We put cosine of 1, sine of 1. That gives us a rho. We go and vote for that one. We, let's say, add 1 vote. This is sometimes called the accumulator. Then we go and say, okay, theta now equal to. We have x, y. We define theta 2. We have cosine of 2 plus sine of 2. We get a new rho. We go and vote for that one as well. And we keep voting for every single point. Now, it's not very hard to see that once you fix x and y, if you vary theta as here or as here, rho changes in a sinusoidal fashion. So that's very easy, and it comes from the cosine and sine. So your votes will look like a sinusoidal fashion for every single point. Remember, now when I go to a second point, I will get more votes, a different sinusoidal. So I will get different votes. And there will be a place, the place corresponding to this straight line, that is starting to accumulate votes. For every point, we are going to have that sinusoidal. We vote basically on that sinusoidal, and we start to accumulate. And now the next step is to go into the accumulator and find the maxima. Maybe multiple if there are multiple straight lines, but we go and find and say, oh, this is the rho and theta that many points like. And that's how we detect these lines. So let me just run you through the pipeline again. You start from the image and you do an edge detection. Every point, some of them in the lines that you care about, some of them outside, every point defines an equation like this. Every point gives you the xy coordinates. So you go into the accumulator space and you vote, sinusoidal votes. Or you just run through the thetas in the discretized space and you vote for every row that you get from this equation. Every point a vote. Then when you finish, you basically say, let's go and look which areas, which basically entries in my accumulator have enough votes. That means that there is a straight line going through them. Now, this concept of voting goes very far, and you can actually do many things beyond detecting straight lines. Let's just show one example. So here we have 5 points, and then the accumulators. So it's just going, and you will see there is a straight line, so there will be 3 votes for that, and there is another straight line. Should be 3 votes, 2 votes, 2 votes, and so on. For this very particular example, I just want to use it to show how we basically get this sinusoidal type of votes for every point. Now let's see that on a real image. So what we see here is an aerial image here, and we clearly see that there are some straight lines. This is the result of edge detection. In particular, it's a canny edge detector. Now, it's a bit confusing from it. We want to get the parametrized straight line. We want to go the row. We want to get the row and theta for this one. This is the picture of this accumulator that went through all these points. Now, you don't need to use all of them. You can just sample some of them. There's plenty of points on the straight line. So you will get very high accumulator just by using a subset of them. But this is the result of the accumulator. And then you go here and you look for the maximum values. And from then you get the row and the theta that correspond to those maximum values. Remember, this is your theta row accumulator. So wherever is the maximum, it gives you a value for theta and a value for row. And those corresponds to what we see here. And then you can put it back on the picture and say, this is my most basically extreme line, my most prominent line. Then there might be other maxima. They will certainly be for this line and this line and this. And you can go and pick all of them. In this case, we are only marking the most prominent one. A very simple and extremely powerful technique. I want to show you also how we do this for circles. But before that, I want to run this example on Matlab. Let's see that. We're now, as we said, inside the Matlab environment. And let's see the type of operations that we're going to do to illustrate the Hough transform to detect straight lines. So there is a bunch of commands here, but I'm going to describe them to you. Most of them are just to make nice plots. I'm going to describe to you those that are important to understand what basically the Hough transform is doing here. So first, as we have seen many times in the past, we read the image. This is the first operation. Then we're going to rotate that image. This is just for the fun of it. I don't want you to believe that we can only detect horizontal or vertical lines. So we're going to rotate that image. Here, we do edges. Remember, the first thing we need to do is detect the edges in the image. That's the input to the Hough transform. And then here it is, the Hough transform in Matlab. That will basically create this accumulator in the theta row space. And these are a bunch of operations just to illustrate, to visualize. We're going to run it in a second. I'm just describing the operations for now. Then the next, we need to detect the peaks. We need to detect the maxima in the accumulator, and that's this operation, and we're going to plot it. Now we have the maxima, which means that we have the row and the theta, and we need to detect the lines. We actually need to draw those lines. And that's what this operation does, is basically finds the lines, and then the rest is going to draw them, and actually it's going to draw them as segments. And with the images, I'm going to illustrate you how we do that. So let's just run all these operations and let's just see the results. So here are the two images. As you see, it's pretty fast. And we see the original image. This is the accumulator. And here the squares, the white squares, are basically the picks basically the most important maxima in the accumulator, and those are these green lines that we see here. Once again, in the accumulator we have rho and theta. Once we have that, we can go back into the image plane and draw the lines. Now you may wonder, but wait a second, rho and theta will give us straight lines but all across the image. How do we get to segments if we need to get to segments? And the basic idea is that there are many ways of doing that, but one way of doing that is you go and put the line back in the image as we have here, and then you can go around that line and see if there are actual points in the image which were detected by the edge detector that voted for that line, and you basically can get what actually was the real segment and not the whole line in the image. That's just one way of doing that. And as we see here, we got these straight lines. Very fast and very simple operation to get straight lines. There are others, just their votes are weaker, and we need to decide to put a threshold in the accumulator. We might put a threshold that says, don't give me any line that has less than certain amount of votes, or we can say, give me the 10 top lines, give me the 5 top lines, or anything that is application dependent. So with this image and with this example, we see the whole pipeline. From the image, detect the edges, create the accumulator, find the maximal, draw those lines back to the image, and if you need, basically find the segments by looking in the image. Where do you have actual points that voted for that if you need just the segment? So now we're going to go back and I'm going to describe what we do for circles. What about circles then? So here we have an image of circles, and we want to know if we can basically find the circles using the Hough transform. The idea is exactly the same. Now a circle can be written down in the following form: x minus x0, that's the x coordinate of the circle, square, plus y minus y0 square equal to the radius square. So every point in a circle holds this equation where the center of the circle is given by this and this. These are the coordinates of the center, what we need to find. And the radius of the circle, which is also an unknown, is given here. If you don't remember this formula, just pick any of the elementary geometry books, or just believe me that this formula is the right formula for a circle on the plane. Now, in the same way that we needed to find rho and theta for straight lines, we need to find the center and the radius for a circle. So we need 1, 2, 3 parameters. So now our accumulator won't be on the plane, it will be a 3-dimensional accumulator, but we are going to do exactly the same. We are going to have an edge detector. Every point is going to vote for circles. Every point is going to give us its coordinates, and then we're going to run through the accumulator on the x coordinate of the center, the y coordinate of the center, and get the radius. So we are going to run through that, through the x's, run through the y's, and then get the radius. We accumulate, we pick the maximal one, and we basically are done. We got our center and radius. So let's just illustrate one example. Here we have the edges, and I want to repeat that once again. Every point here will vote for multiple centers, multiple radius. We can, of course, limit the centers because we know the dimensions. We can also limit the votes for the radius because we also know how large the objects can be in the image. We are going to vote for that. There are going to be multiple votes for the real circles in the images, and then we basically detect them. And here they are. We basically went through the accumulator and find the top votes and we get our results. Basically, the Hough transform can be used for any parametric curve, anything that we need to vote for some parameters of that curve. As rho and theta, the centers, we can find parabolas, we can find any curve that we can write with parameters. Now, the more parameters you have, the more expensive the Hough transform is. So normally the Hough transform is used for finding straight lines, circles, ellipses, relatively simple objects that have a controllable number of parameters. Otherwise, your accumulator space is huge, takes a lot of memory, and takes a lot of computational time, both to compute it and to find the maxima. But for those simple shapes, there's one of the best techniques out there is the Hough transform. So I hope you enjoyed this video, and I see you in the next video. Thank you very much.